I want this to be very clear in your mind. When can we use parallel axis and perpendicular axis theorem? Be very clear with this. So first thing is parallel axis theorem. The formula you guys know. Application is universal. You pretty much can use it with everything and anything. But of course, there is a condition. Condition being the axis must be parallel to the one through the center of mass. That is, I can have any shape and I know the center of mass is over here, and through that what I have is it rotating. Now if I shift it, if I have a new axis of rotation, it has to be so. See, I'm copying over here and pasting. It has to be so. It has to be parallel to it. It need not be over there itself. It can be anywhere. Even this is okay. Even this is okay. Even this is okay. Even this is okay. Even this is okay, to be honest. So you need to be very clear when you can use it, when you can't. So this too has to be, and it is parallel. I just copied it, right? Copy, paste. So it has to be parallel, and yeah, it can be clockwise, anti-clockwise, whatever you guys want to think of. That is possible. So parallel axis theorem can be used pretty much everywhere. So the axis condition is that axis must be parallel to the one through the center of mass. If you want to say you are looking at rotating an object in this axis, so you need to know the moment of inertia through the center of mass with this condition. Okay guys, so you please understand that it need not be just up straight. It can be any direction, whatever you guys want it to be. Got it? Then what do we have? Then key requirement is distance. D is the perpendicular distance between the two parallel lines that you guys know. So that's D is over here. I use capital D. Here I have by mistake type in small d. Doesn't matter actually. Not a big deal. Usage cannot be used. Okay. We cannot use it for non-parallel axis. So I can't have this information and try to figure out this. That's not possible. Okay. Now let's look at perpendicular axis theorem. Perpendicular axis theorem has a lot more limitation. It's a limited one. Here it is universal. It's limited. It's valid only for laminated flat two-dimensional object. Okay. So we defined laminary, sorry. We have defined this. So keep this in mind. Now, axis must be mutually perpendicular and intersecting at a common point. Object must lie entirely in a single plane and cannot be used for three-dimensional object like sphere, cylinder, or thick disk. Okay, all of this has to be kept in mind. So with perpendicular axis, we saw this in the video, but please see to that you don't miss this out. That's why I'm making an exclusive video on this. So this has to be very clear. Now you have a laminar structure, and you need not be at the center itself. It can be here also, not an issue. So I know the rotation along any two axes. Of course, they are mutually perpendicular to each other. So I know the moment of inertia trying to rotate along this axis, and over here I can figure out this. I can figure out this. I mean, I can do this and this, and I can know this too, and I can figure out this. It can be anyhow and anyway. Right? So pause, copy this, don't miss out anything. Okay, I'm not very comfortable with this as in letting this open. So laminar objects, let me start from here. Again, remember this, laminar objects are those where the mass is contained almost entirely within a single plane. Okay. That is basically the thickness, that is K by the way. Okay, let me rewrite this. Thickness is negligible. So you can ignore it in that way. Negligible compared to its length and width. Right? So keep this in mind. It's applicable to only to that. This is a case of not possible. Okay, you can't do this. This is given and you're trying to find this. It's not possible. And this is your perpendicular axis. Okay.